Welcome to the Explainer. Today we are tackling an absolute classic from physics, the fundamental equation of rocket motion. We're going to see, step by step, why the simple physics you might have learned in high school isn't quite enough to get us into space.
Right, so we all learn F equals ma. It's like physics 101, isn't it? Force equals mass times acceleration. And hey, it works perfectly for things like a car or throwing a ball, anything where the mass stays the same. But a rocket is a totally different beast. It's constantly throwing its own mass out the back as high-velocity exhaust. And that single crucial fact, a variable changing mass, means our simple F equals ma just breaks. It's not the right tool for the job.
So here's our game plan for deriving the real rocket equation. We'll start by defining the exact problem we're trying to solve. Then, we'll revisit Newton's second law, the real one. After that, we'll carefully define our system, track its momentum, put it all together to get the equation, and finally, make sense of what rocket thrust really is.
Okay, first things first, let's lay out our mission. We're solving problem 1.178 straight from the source text, which basically asks us to build the equation of motion for a rocket from the ground up.
So our goal is to prove this exact equation. Let's just break down what we're looking at. M is the rocket's mass at any given moment. And remember, it's changing. W is its acceleration. F is any external force, like gravity or air resistance. And the new players here are mu and U. Mu is just how many kilograms of fuel gets shot out the back every second, and U is the speed of that exhaust relative to the rocket itself.
So the whole reason our old friend F equals ma fails us here is because it's actually just a special case. It only works if mass is constant. To handle a rocket's changing mass, we have to go back to the source, to Newton's more general and, frankly, much more powerful second law.
And this slide really shows you the key difference. On the left, you've got the simplified version we all know and love. But on the right, that's the real deal. Newton's true second law says that force isn't equal to mass times acceleration, it's equal to the rate of change of momentum. And it's that focus on momentum, not acceleration, that's going to be our master key for solving this whole problem.
So what even is this momentum p? Well, it's actually pretty simple. It's just an object's mass times its velocity. The big idea here, the reason this is so powerful, is that the general law tells us that any external force on a system changes its total momentum over time. We're going to use that exact principle to figure out how shooting fuel out the back changes the rocket's motion. Okay, this next step is absolutely crucial, and I mean it. This is the single spot where most people get tripped up when they first try to solve this problem. We have to choose our system. What exactly are we keeping track of? The choice we make here is everything. So here's the clever part. We're going to zoom in on an infinitesimally small slice of time. We'll call it dt. At the very beginning of that tiny instant, our system is simple. It's just the rocket and all its fuel. But an instant later, at time t plus dt, our system has to include two things, the now slightly lighter rocket and that little puff of gas it just ejected. By including the ejected gas in our system, we've created a closed system. No mass has secretly escaped, it's all accounted for. And that allows us to track its momentum perfectly. Great. Now that we've carefully defined our system, we can actually write down the math for its total momentum. We'll look at the before picture at time t, and then the after picture at time t plus dt. At time t, the before, it's super straightforward. The total momentum of our system is just the rocket's mass times its velocity. Easy enough. Now for the after picture. This looks a little more complicated, but it's really just two pieces added together. First, we have the momentum of the rocket itself. Its mass is now a tiny bit less, and its velocity is a tiny bit more. Then we have to add the momentum of that little bit of gas we just ejected, which has its own mass and its own velocity.
And here we are at another classic stumble point. What is the velocity of that gas, v gas? Well, the problem tells us the gas is ejected with velocity u relative to the rocket. But we're not on the rocket. We are a stationary observer on the ground, so we need its velocity relative to us. Think about it. If the rocket is already moving forward at v, and it shoots gas backward at u relative to itself, then from our perspective on the ground, that gas is moving at a velocity of v minus u.
All right, we have all the ingredients. We've got the momentum before, we've got the momentum after, and we have the correct velocity for the gas. It's time to put it all together, bring in Newton's law, and see what we get.
So first, we find the change in momentum, dp, which is just the final momentum minus the initial momentum. Now, if you expand all the terms, it looks like a bit of an algebraic mess.
But a bunch of terms cancel each other out, and one term is so incredibly small that we can just ignore it. And what we're left with is this beautifully clean and simple expression for the total change in the system's momentum.
Now, for the magic trick, we bring back Newton's general second law. The external force, F, is equal to the rate of change of momentum, dp, divided by dt. So we just take that clean expression for dp that we just found and divide the whole thing by our tiny time interval, dt.
And when we do that, look what we have. These little fractions should look really familiar. dv dt, the rate of change of velocity, well, that's just the definition of acceleration, which the problem calls w. And dm dt, the rate at which the rocket loses mass, that's the gas discharge rate, mu. So we just swap in those definitions and we get F equals mw minus mu. And if we just rearrange that a little bit to solve for the forces acting on the rocket, mw, we get mw equals F plus mu. We did it! We derived the equation. Wait a minute, hang on. The problem in the source text asked us to prove mw equals F minus mu. It has a minus sign. Do we make a mistake somewhere?
Nope. The good news is we didn't make a mistake at all. And this little confusion over the plus or minus sign is actually the perfect way to understand the physics of what thrust actually is. It's all about being careful with our vectors. Let's be super precise here. The source defines U as a vector. That means it has a direction. It's the velocity of the ejected gas relative to the rocket. So if our rocket is moving forward in the positive direction, then the vector U is pointing backward in the negative direction. That direction is key. So let's look at our equation. mw equals F plus mu u. Since the exhaust vector u points backward, it's actually a negative number. That means the term mu u is a positive force pushing the rocket forward. That is the thrust. Now the version in the textbook, mw equals F minus mu u, is just a different convention for writing the exact same physical reality. In that version, u is treated as the exhaust speed, a positive number, and the minus sign is put in manually to make sure the thrust force points forward. So negative mu u as a whole becomes a forward-pointing vector. They both describe the same thing. The net force on the rocket is the sum of external forces plus the forward push from the thrust.
And that's really the power of what we just figured out. This equation is like a snapshot. It tells you the rocket's acceleration at any single moment. So what if you wanted to find out the rocket's final velocity after all the fuel is gone? Well, you would have to integrate this equation over the entire time the engine is firing. And that process, well, that leads to another legendary result called the Tsiolkovsky rocket equation. But that, my friends, is a deep dive for another explainer.